Hi everyone. Today we'll practice using the limit definition of the derivative to find derivatives. First, we must recall what the limit definition said. If you would like to try the next exercise on your own, download these notes using the link in the video description. I believe we know two equivalent limit definitions of the derivative of a function f at a. If you want to compute the derivative of f at a, you can compute the limit as x goes to a of f of x minus f of a divided by x minus a. Or, equivalently, to compute the derivative of f at a, you can compute the limit as h goes to 0 of f of a plus h minus f of a divided by h. Today I will show you how to use the first limit definition and how to use the second limit definition to compute derivatives. In the next problem, we must find the derivative of x squared at x equal to 5. If you would like to try this problem on your own first, this is a good time to stop the video. For this problem, I will use the first limit definition, and in the second problem, I will use the second limit definition. Because I must find the derivative at 5, I will replace a with 5 in my definition, and I will get f prime of 5 equals the limit as x goes to 5 of f of x minus f of 5 divided by x minus 5. Unfortunately, I cannot plug in 5 to this expression to compute the limit, because then I get 0 in the denominator and I get f of 5 minus f of 5 in the numerator, which is also 0. This is of the indeterminate form 0 divided by 0, which suggests I need to apply some algebraic manipulations before I compute this limit. Thankfully, I know the formula of f, so I know that f of 5 is 5 squared. Also, f of x is x squared. So I can rewrite this limit as the limit as x goes to 5 of x squared minus 5 squared divided by x minus 5. This allows me to factor the numerator, and I get the limit as x goes to 5 of x minus 5, x plus 5 divided by x minus 5. X minus 5 in the numerator divides out with x minus 5 in the denominator, and I get the limit as x goes to 5 of x plus 5. Nothing stops me now from plugging in 5 to compute this limit. When I do so, I get 10. So the derivative of this function at x equal to 5 is 10. I have one more problem for us. We need to find the derivative of 3x plus 1 at x equal to 2. If you would like to try this problem on your own, stop the video now. This time, I will use the second limit definition of the derivative. Because I want to compute the derivative at 2, I will replace a with 2 in my definition, and I will get f prime of 2 equals the limit as h goes to 0 of f of 2 plus h minus f of 2 divided by h. Just like before, I can't simply plug in 0 to this expression for h, because then I get 0 divided by 0. Instead, I plug in the inputs to the formula of my function. When I plug in 2 plus h into the formula, I will get 3, 2 plus h plus 1. I simply replaced x with 2 plus h. When I plug in 2, I will get 3 times 2 plus 1. Note that I put the entire expression in parentheses because I want to subtract the entire f of 2. So I'm subtracting everything I get when I plug in 2 to the formula. Now I can simplify the numerator by multiplying out the first parentheses and by distributing the minus into the second parentheses. And I get 6 plus 3h plus 1 minus 6 minus 1, everything divided by h. I see that 6 and negative 6 go away, 1 and negative 1 go away, so what I have left in the numerator is 3h. In the denominator I had h. This allows me to divide out h, and I get the limit as h goes to 0 of 3. The limit of a constant is that constant, so this limit is 3. The derivative of this function at x equal to 2 is 3. Note that this answer makes sense. This is a linear function, and we know that the derivative of a linear function is its slope. So the derivative of this function at any point should be 3. We confirmed it by using the limit definition. We obtained that the derivative indeed is 3. One more problem. We must find an equation of the line tangent to this graph at t equal to 1. If you would like to try this problem on your own, stop the video now. We must find an equation of a tangent line. We know that tangent lines are straight lines, so they have the formula y equal to mx plus b. We also know that the slope of the tangent line is the derivative. So I know that the slope of this tangent line will be the derivative of the original function. So to compute the slope of the tangent line, I will compute the derivative of f at t equal to 1. So I will use maybe the second limit definition of the derivative, and I get f prime of 1 equals the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. I plug in those inputs to the formula of my function, and I get the limit as h goes to 0. When I plug in 1 plus h to my formula, I will get 1 plus h squared plus 2 1 plus h. This is what I get when I plug in 1 plus h for t. I'm supposed to subtract f of 1, so I subtract what I get when I plug in 1. Subtract 1 squared plus 2 times 1. I divide everything by h. I simplify the numerator by multiplying everything out. In the numerator, in the first parentheses, I multiply this out, and I get 1 plus 2h plus h squared. Then I'll multiply 2 out, and I get plus 2 plus 2h. Finally, I distribute the minus to both terms, and I get minus 1 minus 2. Everything gets divided by h. Few things cancel. 1 and negative 1 go away. 2 and negative 2 go away. Also, 2h and 2h, when I add them, I get 4h. So I get the limit as h goes to 0 of 4h plus h squared divided by h. In the numerator, both terms have h in them, so I can factor that h. And I get the limit as h goes to 0 of h 4 plus h divided by h. This allows me to divide out h, and I am left with the limit as h goes to 0 of 4 plus h. Nothing is stopping me from plugging in 0 to this expression, and I just get 4. This means that the derivative is 4, which means that the slope of the tangent line is 4. The formula of the tangent line then must be y equal to 4x plus some vertical intercept b. To find b, I need to plug in some point on the graph of the tangent line and solve for b. Thankfully, I know one such point. I know that the tangent line and the original function touch at t equal to 1. At t equal to 1, the value of the function is 3. When I plug in 1 here and I plug in 1 here, I get 1 squared plus 2, that's 3. So both functions, the original function and the tangent line, share the point 1, 3. I will plug that point in to this equation. So I plug in the point of tangency 1, 3, and I get 3 equals 4 times 1 plus b. 4 times 1 is 4. I subtract 4 from both sides and I get negative 1 equals to b, which means that the formula for the tangent line is y equal to 4x minus 1.